Okay. All right, so we started off with just the basic vocabulary for the unit, and then we watched the thing about the manatees, and then we talked about types of association. This unit focuses on linear associations. All right, so that's where we're at on page 6. Hello, friends. Just grab a straight edge. You don't need a calculator. Corey should be right behind you, I hope. Unless you took a detour. All right. All right, so here we go. All right, so when we have our scatter plots, we are going to be focusing on linear rather than looking at other types of patterns. So when we focus on our linear associations, we can describe those associations by strength and direction. So when we talk about strength, just grab a straight edge and you'll be ready to go. Yep. When we talk about strength, typically we focus on using the words strong. We also have moderate and weak. But if it's not a strong relationship, why in the world are we studying it anyways? Perfect if everything falls exactly in a straight line, which is highly unlikely with data. Okay.
But that would be a perfect correlation.
Yes, you're right. That's what makes a perfect correlation. Direction is positive or negative. And then no association, of course, can be kind of in there when there's nothing going on. Okay, so positive, of course, means we're going uphill. That's positive, and so you can connect that idea to what you know about slope. And then negative, of course, is going downhill. Or we can also refine that as the explanatory increases, the response variable increases or decreases. So we'll be using some of that language. Now, mathematicians do really love to have a number to go with those words as like evidence of saying something is strong or weak or moderate. So there is a calculation called the correlation coefficient. There is no units on that, so it's not like you measure correlation coefficient in inches or miles or kilograms. It's just a number. And it's kind of like a rating number, but it's not out of stars. The rating numbers for correlation, which is calculated, fall between -1 and 1. And so positive values are positive and negative values are negative. But what's kind of interesting is that when we're around 0, that's when there's no correlation. And then we also have that idea of weakness, right? Being weak on either side. Okay. When we get to a high correlation, whether it be negative going downhill or positive going uphill, that's when we have strength, or our correlation association is strong. And like Mark said, when we have our lines perfect, or our data points perfectly in line, that's when we have perfect correlation or association, and it's +1 or -1. Okay, so you should have had some experience with correlation coefficient in Algebra 1, but that was a long time ago, right? So long. You were little people back then. All right, so let's turn the page, and we're just going to do a quick sorting activity on this next page. Can you figure out what the correlation coefficient is? All right, so to kind of guide this, the easiest way to get started is to, first of all, look at the graphs. Can you guys tell that some of the graphs are kind of going in an uphill organization, a downhill organization, or just completely scattered, right? And you could look at like the tightness of the points. With your straight edge, if you wanted to attempt to draw lines, then you could, but you don't have to for this activity. Now, up here are a whole bunch of numbers that are correlation coefficients that go with these, but they're disorganized. And so to help us kind of understand, once again, what correlation coefficient is, let's make a number line at the top of our paper with -1 at one end, and then we're going to go and then +1 at the other end, and 0 is here in the middle. Okay, I'm going to zoom back in so you can see what I'm doing. Okay. And now what we're going to do is just put those numbers on the number line so we can think about where they fall in weakness and strength. So I'm going to look at the positive ones first, and there's actually some nice patterning here. So positive, we have 0.7, 0.5, 0.9, 0.1, and 0.3. Hey, they're all odd numbers, aren't they? Let's make our lives easier. So, of course, closest to 0 is 0.1. And we're just kind of estimating where they go. It doesn't really matter. Okay, so just plotting those in there. The thing that's important with this is that we're looking at the order they go in and how close they are to the value of positive 1. Up here is strong, right? Down here is weak. So can you do the negative numbers on the other side? Place those values. I think there's 4 of them left.
Yeah, here's the thing. There's 9 boxes and only 8.
There's 4. We have 5 values total. We do. There's 5 on this side and 4 on that side.
Okay. No problem.
It's okay.
No, it's like I noticed that there's one that's like 100, and that's probably that 0.
Yes, yes. So where is the negative 0.8 going to go? Is that going to go at this end?
No.
No. Okay, so it's just, that's one of the things to be considerate of, is it, even though it's negative, it actually is the strongest negative correlation coefficient listed here. Okay,
Yeah,
so negative 0.6.
Yeah, you just get rid of that negative part, and it's like, okay, just put on the left or right.
Yes, kind of like that idea of absolute value. 100% correct. Okay, so that means this is also kind of in the weak zone. Okay, so remember, weak is closer to 0, or no association is essentially closer to 0. It depends what you're analyzing. It possibly, you might be switching up your words just a little bit. Okay, so now I'm going to zoom out. The easiest ones to determine are the ones that are closer to the ends, the strong on either side. So let's go with the 0.9. Which graph is going to be the 0.9? It's the strongest. Bottom right. Very good. So R equals 0.9. Keep putting R equals. That will remind you that correlation coefficient is the R. Okay. So then I'm going to kind of tick them off going from strongest in. Where's the negative 0.8? Top left. All right. So now let's do the positive ones, 0.7 and 0.5. So we're looking over here. And this is kind of like, which one do you think is stronger? Do you think this one's stronger or the one above it? The bottom one. So R equals 0.7 and R equals 0.5. Once we get below 0.5, it's kind of like, the points are getting really spread out. But we should have another negative one that's halfway decent, negative 0.6. Yeah, I think it's this one, right? R equals negative 0.6. And probably this one is the 0.4, right? The negative 0.4. Okay. And then we're kind of left with these ones in the middle that don't really have much associated going on, which means,
1, 3.
yeah, so it really might not even matter, honestly, that we label these. Now, you might still think that 0.5s are kind of not even that strong. But if like you're looking between some sort of a connection to figure out why a disease is happening, right? And you don't know why, right? You're looking for associations with anything, right? when COVID first started, it was like, does it travel in the air? Is it by touch? Is it a liquid? Like, there was a lot of concern about how that how it was spreading. And so they were looking for all sorts of association, as well as being very careful in the beginning until we understood how the virus worked. So at any rate, these lower associations do have value because they just start to give us clues. Of course, we love it when we have really strong associations. That's a beautiful thing. All right, so lesson 1 was kind of just there to jar your memory on stuff that hopefully you already have some knowledge with. And now we're going to go a little bit deeper into it. Let's go ahead and turn the page, and we're going to do some scatter plots. Now, scatter plots are kind of annoying to make because you're just plotting points. Some people find them meditative because you're just in the zone, plotting points. Life is good. Accuracy still matters. And of course, we're going to eventually just rely on technology to do the work, because why wouldn't we let technology do the work? So I'm not ever going to have you be quizzed on making a scatter plot. Does that make sense? By hand. That's not a good use of your time. But basically, let's go ahead and look at this example, make sure we understand the context, and then we'll make a scatter plot that follows all of our directions of, title, tick, tick, label, label, label. All right, so alumni affairs at a small college. So when I think of a small college in the area, I think of like Roberts or St. John Fisher, right? Nazareth. A alumni affairs director at a small college wants to determine whether there is a linear relationship between the number of years alumni classes have been out of school, how long ago did they graduate, and their annual contributions in thousands of dollars. So when you graduate from a college or university, there's this whole alumni foundation, which then raises funds for scholarships or projects on campus, et cetera, and so on. I get mail and email from both Purdue University and Fisher. And they're like, do the fund. And then the thing is that we also have days in the year that are kind of dedicated to that. So when people go to homecoming at different, their colleges, that might be a big alumni activity on your different graduations, so like 15-year reunion, 20-year reunion. There's also, we know about Black Friday, right? And then there's Cyber Monday, and then that Tuesday is Giving Tuesday. And that's when all sorts of nonprofits are asking for donations as part of the gift giving season, if you can do it. And it's not easy to have extra funds. Okay, so here we go. The data shown in the table, on the right. Display the scatter plot and determine the type of correlation. All right, so let's make sure we understand the data. We have new vocabulary. Our X variable is called our what variable? It begins with an E. So it's on page 3 of your note packet. Thank you very much. It is the explanatory variable. So what we're hoping is that the number of years out helps to explain the amount of the contributions. And so the contributions are responding to the years. So this is our response variable. So this is new vocab that we need to master because it can be used in a multiple choice question or in explain the relationship between the explanatory and the response variable, right? Okay. So now let's take a look at, we have only positive numbers. This table, remember, the numbers are holding hands, right? 1 year out of school goes with 12.5. So we should do no sorting here, right? These are coordinate pairs. However, we do want to look at the range of values. So looking at years out of school, what's our highest number? 30. And our lowest number is 1, right? So do you think we need a break in our axis? No. We need to make sure we go up to 30 though, right? So our axis is going to go from 0 to 30. And that's the x-axis. Okay? All right, let's look at our y values. So we do have decimal points we can estimate. What's our largest value? 14.6. Our lowest value is 2.7, still pretty close to 0. So essentially for the y-axis, I mean, I'm not going to go to 14 point, I'm going to go to 15, right? So I'm going to go from 0 to 15. So when we think about skip counting, we might think about, 5s, 10s, 15s for both of those, depending how we have information. All right, so one of the reasons why I asked you to grab a ruler is because you always want to mark off your borders for your grid. Do we need any breaks? Not at all. So what I'm going to do is I'm going to take my straight edge and I'm going to draw in my x-axis. Bless you. And I'm going to draw in my y-axis. And I got that ready to go. Does anybody need a straight edge? Did anybody get one? Everybody's got one? There we go. All right. Here you go, Bryson. You're welcome. All right. So I'm just drawing in those border lines. So life is good. All right. And now we kind of have to think about how we're going to tick off our axis. We can also label our axes. So the x-axis is number of years out of school. Whoops. Let's go with that. There we go. Number of years out of school. And I'm definitely starting at 0, and I have to get to 30, and there are not 30 blocks. But it looks like there might be 15 blocks. I'm wondering if this is one where I can go 2, 4, 6, 8, 10, right? That's been a pretty popular one. So 2, 4, 6, 8. At the 5th block, I can make a 10. Then 20 years out, and then 30 years out. And that axis is ready to go. All right. The y-axis is annual contributions. And I'm going to erase the word in. I can just put, 1000K like that if I want to, right? Yeah. And then what's nice about this is 15 is half of 30. Can we use the same kind of marking off on our axis? Just go 5, 10, 15? Yeah. So 0, 5, 10. And then I'm the type of person that before I start graphing, I am going to make sure I have completed the outside of my graph. So the one thing I have left to do is my title, right? So I'm going to take care of that. And this might be alumni. I mean, it says annual contributions. I might put alumni up here, alumni contributions as my title at college or university. Univ. We don't have a university name. ABCD University. Okay. All right. So now we're ready to plot points. And the points aren't going to necessarily be on grid lines whatsoever. So I'm going to zoom into my graph. My very first point is 1, 12.5. So 1 falls in between the 0 and the 2 line, right? That's the 2 line. So I'm halfway in between. Now I got to go up to 12.5. 10, 11, 12. It's right in the middle of that box. You're just estimating where it is. Try to get it pretty close, but once again, 0.6, 0.5, we're not going to worry about that. So see if you can plot your 7 points. Hey, how are you, Sam? Good. Yeah, for sure. Do you mechanical or the other kind? Mechanical? Yeah, give me just a second. 2.7. Okay, there you go. Okay, so get you this. We're on page 8 of our note packet. Okay. There's that. Yeah. That's the only way to chart in here. Okay. Okay, did everybody get their 7 points? Okay, so did anybody connect? Now, I'm not asking you to. I'm asking if anybody did. Did anybody connect their points? No. You do not want to connect your points. The reason why is because this isn't what's called a time series. If we were looking at, hey, what's my profit each month over from January to December, that makes sense to connect your points, right? Because you're looking at that data bounce up and down. Here, it's a collection of data, and we're looking for an overall what happens. So clearly, can we see if it's positive or negative? Yeah. Now, do you guys think that it is linear? I think it does look fairly linear. So take your straight edge, and we're just going to estimate where we think the line should go. It's not necessarily a right or wrong answer, although, like, I wouldn't necessarily put my line there because I only have 1 point above, right? And all the other points below. So you kind of want to play with your straight edge and see where should I put it. So some points are above and some points are below. And maybe I might need to actually redraw it because my computer doesn't work well, play well with others. I kind of like that. Now, there is a point that I have that's fairly high. Okay, great. This point is fairly high above the line. It's at the 5-year reunion, and maybe there's activities where, people feel nostalgic and go back to campus. There's also points that are below. Nothing is really extreme, though. You can have outliers in this graph. Okay, so we can say that there is, do you guys think it's strong, or do you think it's more moderate? Moderate. We don't have enough data maybe to put the strength word to it. So we have a moderate, negative. Hi, hon. I did not see you. I thought I do not see it. So I thought you either carried it out. Okay, you have a good day too. Moderate, negative, linear. And you can use the word association or correlation. Doesn't matter. I'm going to put correlation. We do not know the correlation coefficient, and that's okay. Okay? We're going to learn how to calculate that, and of course, then we're going to rely on our calculator to produce that number for us in the future. Well, understanding where it comes from is kind of a neat process. Now, the other thing you could say is that maybe this could be more of this kind of pattern, right? What's that pattern? What do we call it when something starts to drop off quickly but then balances out? It's not slope. It's exponential. Exponential decay. Exponential growth. Remember how it starts off slowly and then it flies up? That's exponential growth. So you might be that, and then eventually, of course, maybe all the alumni will pass away. Woo, sadness, right? Or they're paying for their own kids' tuition. There's all sorts of reasons why this amount of money will decrease. So at any rate, you could argue if we had more data that it's not linear, that it's actually exponential decay. We don't have enough data, okay? But we certainly can tell some sort of relationship is going on here. All right, so let's go ahead and turn the page. We're going to do another one by hand, and this one's bigger, but we're going to just chill out for like 10 minutes and do it. Before we do it, though, let's talk about what it is and set it up together. Okay, so when you turn the page, whoa, man, look at all this data. So it's going to be a lot more than 7 points. No big deal. You're just plotting points, people, right? You can handle that. All right, so you're going to plot them eventually. Here, just hold on. We're going to chit-chat. No, because we're all going to set up our graphs together.
That's a lot of work.
Just trust me for a minute, okay? Right? We went over, did we measure arm span and height the other day?
Yes.
And that is an interesting relationship that's out there. Now, the reason why I like to do this activity with multiple grade levels of classes is because it gives me a chance to talk about a very famous Olympian named Michael Phelps.
I don't know who that is.
Okay, Michael Phelps is an award-winning Olympian in swimming, men's swimming. So this is a very short 3.5-minute video that definitely falls under the category of Saturday morning TV, or, you know, it's not scientific really, but there is some interesting points to make. Good morning. So we're going to watch this, then we're going to set up our graph, then you're going to have like 10 minutes to plot. Take your time, right? We have to talk about why breaks in the graph are so important for this graph. So I hope those of you that are speeding ahead, you're waiting for some of it. Okay, here we go. One video, 3.5 minutes long. Here we go. So,
with a total of 28 medals, Michael Phelps is the most decorated Olympian in history. At the height of his career in Rio 2016, he had already won 23 gold medals, more than twice the number of the second highest record holder. Phelps can fairly be described as a Superman, and is basically the Lionel Messi of swimming. The question is, what makes Phelps so good at swimming? In short, his combination of genetics, willpower, and skill has led to his enormous success. Phelps has an unusual ergonomic efficiency in the pool, giving him an advantage over other competitors. His extreme advantage is due to his somewhat freaky body structure. First of all, he stands tall at 6'4", which is the ideal height for swimming. His arm span, however, is 6'7", 3 inches more than his height. Generally, a person's arm span is equal to their height, but Phelps is no ordinary person. This anomalous characteristic provides him with an absurd amount of pulling power in the water. Basically, his arms work as powerful, propulsive paddles in a more efficient way than anyone else in the pool. Additionally, his upper body is that of a 6'8" man, giving him an amazingly long reach with every stroke, which pulls him through the water even faster. Surprisingly, his lower body is that of a man only 5'10", which is actually beneficial, as it reduces resistance in the water. Phelps has huge palms that support his paddling ability, along with size 14 feet, which essentially act as flippers. This giant set of feet is attached to extremely flexible ankles, which work like fins, just like a shark. Now, when the human body performs physical activity, it produces lactic acid. This substance causes fatigue and slows down muscle contraction. To prepare for another round of physical activity, our body must first flush out this acid. To do that, it needs a certain amount of recovery time. Athletes often envy Phelps because it's scientifically proven that his body produces half as much lactic acid as his rivals, significantly shortening his recovery time. That said, 2 phrases should not be forgotten: dedication and hard work. Saying that someone is born to win is an absurd claim, but having an innate desire to win is far from impossible. His extensive medal collection resulted from the endless hard work and dedication that he put into his training each year. 6 hours of training 6 days a week is no joke. Michael Phelps spends a lot of his time training in the pool, adding up to a whopping 80 kilometers each week, which is more than 13 kilometers of swimming on each training day. Besides this huge amount of time in the pool, he also spends a lot of his time in the gym. To fuel all this activity, a superhuman like Phelps requires a superhuman diet. Phelps consumes 12,000 calories per day, while an average person requires 2,200 to 2,700 calories, depending on their body structure. This enormous calorie intake is necessary to balance all the calories he burns during his training to ensure that he doesn't lose weight. So remember, Phelps' success is based primarily on his training, while his genetic advantages are only a secondary bonus. The question is, will we ever see another athlete of his caliber in the future?
So it is really fascinating how, like the proportions of his body, his lower half is like of a 5'10" person, right? Versus his upper half is like 6'8". And then the thing about the lactic acid is also very interesting. I wish we had some more data there where that resource came from, because that's fascinating. He doesn't require as much rest in between, and he does compete in a lot of different categories, which therefore gives him that advantage. All right, so we did that, and then this data is not your data. This is from last year, my group. So let's kind of just take a look. Once again, you have to plan. Now, let's look at our different heights. Okay, so kind of just skim those numbers. We're going to use height on the x-axis. What is our shortest person? How many inches? 59. Okay. And what about tallest? 75. Okay, so we need an axis, and then this is where the calculation of range is actually extremely helpful. If we subtract those two numbers, that's a range of 16, right? So we need to be able to have like 16 boxes. So the range is 16. Okay, so now let's do the same thing for the y-axis, which is going to be our arm span. Okay, smallest arm span. 57. Okay. Largest arm span. There's an 84. That's what I say too. Yo! So I don't remember who that is, number one, or if that is an error, two, or somebody who's like, haha, you know what I mean? Like, I don't know. But we'll see what that does visually to our scatter plot, okay? Now, what is that range? That range is going to be 27, right? So it's possible we're going to use different counting methods on the two axes. We have to make that decision. Okay? All right. So let's go and work on the x-axis first. So once again, you're going to draw in your axis using your straight edge. This is going to be height in inches. Should we start at a height of 0? Is that a good use of our graph space? No. So this is a perfect opportunity to put a break in the graph on the x-axis. We're also going to use a break on the y-axis. Like I said, we don't want to see people with a height of 0 and an arm span of 0. They are still in the womb, okay? So now, we need to be able to get from 59, right, up to 75. So I think we have enough boxes to count by ones. Do you guys agree with that? Okay, so instead of putting 59 on here, I think I'm going to put the number 60 right here, knowing that 59 is the line before it. Does that make sense? Yeah, I have a line for 59. I'm good to go. So now let's make sure we have to get up to 75, right? So 1, 2, 3, 4, 65. Yes, I should be able to do it. So this is going to be 65. This is going to be 70. And this is going to be 75, and I actually could have shifted it just a little bit, but I'm happy with what I have. Okay, and that's nice, easy to work with. Since there's only whole numbers up there, everything at least is going to be on a vertical grid line. All right, now let's go to the other axis. Okay, so I'm going to use my straight edge to draw it in. This is arm span in inches. And this one I need to be a little bit more careful on to see how I should count it off. I definitely want to put a break in that axis, so I'm going to go ahead and do that. So like the breaks are overlapping with each other, and that's okay. It doesn't have to be super neat. But we have to get all the way from 57 to 84. I don't think we can count by ones, right? So we're going to count by twos. All right. So if I need 57, I'm going to say that this is 58, which makes this one 60. So I'm going up 3 boxes to put 60. Does that make sense? And then this is 58, 57 is one below it, or halfway through. Okay, so 62, 64, 66, 68, 70. 72, 74, 76, 78, 80 inches. And then you can label off 90 if you want to, but you definitely have room for the 84. Okay. And for a title, I mean, we can just put height versus arm span sample of high school students. Sample of juniors and seniors, actually. Junior, senior, high school students. Good enough. All right. So you're going to just go slowly and graph all the points. There's enough points there, so if you graph one wrong, it's okay. I'm going to put on some nice chill music while we graph. On spreadsheets. It's okay. I'm not yet. I'm just kind of discussing. I have a couple people still working. I'm okay with that. So are you copying mine versus plotting the points? Yep. Because it is right there. Wouldn't want you to hurt yourself. Anyways, I'm teasing. Okay. So we have about 9 minutes left in class. Let's take a pause. Okay. What do you guys think about this association? It is strong, for sure. And it's positive, isn't it? Yes. So there is a, whoops. There is a strong, positive, we need another word, linear, because you have to say it's linear and not something else, right? It's a strong, positive, linear correlation or association between height and arm span. Okay. Now, I want you to put your ruler on this one. Okay. And draw in a line. So, I want you to tell me though, do you guys think, how much do you want to consider this point up here? Not that it's, so there's a possible, like this point could be an outlier. Like I would have to double check that person's data. It could be a mistake. If it's an outlier, the linear regression / correlation coefficient would consider it when drawing the line, then pulling the line up, right? If it's an error, you would pull it out of the data. Okay? Don't want it to affect your data. So, I'm going to play around here, but I'm going to try to get points above, points below, maybe something like that. Like I said, I don't know if I did it really fast without eyeballing, doing too much work here. I do have this person down here, which I do think is valid, and might pull the line down a little bit. When we actually do the regression line, there is a calculation that it's doing in its head, and that's how it makes the line perfectly located. A couple other things. Something that's different with this graph. Could we, based on how we've graphed it, we could estimate the slope, right? We do a rise and a run and estimate that, but we can't get the y-intercept from the graph. On the other one, and so I'm going to scroll backwards. Oh, do you know what? This one, can we tell what the y-intercept could be? Right around 13,000?
Yeah.
So that one we could actually work as a slope and a y-intercept and write an equation that would be predictive. All right. So our regression models, our equations are going to be predictive models based on data that we can then use to predict future data. All right. So this is a good place to stop. I have no homework for you tonight.